Lecture 9 today, as well as Lecture 10 on Monday, and a review next Wednesday for the exam are really important. A lot of really key concepts to calculus. Lecture 9a, we're going to do the ideas of limits and continuity in the context of examples. And then in next Lecture 9b, it does get tougher. We get more theoretical. We do precise definitions of limits and continuity and rigorous proofs. Okay? Before I get into that, I do want to show you the Mathematica I talked about the other day with sinusoidal modeling. And I also want to write down this equation that you see here. So I was trying to model the length of a day, really daylight, in Minneapolis over the course of 2019. The day number goes between 0 and 365, and the amount of light in the given days varies between a little less than 9 hours to a little bit more than 15 hours in the summertime. And the formula here that is an approximation for the data that I found online that I forgot to share with you, so I still have to share it with you here, is it gives you an amplitude, a trigonometric model that's approximately 3.3456 sine of 0.0174 times t minus 79.88, and then plus 12.191. And I've got the data in Mathematica today, plugged in such a way that I can now do a manipulate that's got 4 different parameters, A, B, H, and C, representing the amplitude. B is that angular frequency, I called it. You don't have to worry about that, what that means. H is the horizontal shift. It's to the right in this case of a sine wave. And C is the vertical shift. And I noticed that I picked values of A, B, H, and C that you see here that are different than what's up here. This plot is actually different than what's on the PowerPoint as well. This graph you can see the red dots a little bit more clearly, especially over there. Okay, you can see that those are really the data points. The blue graph is the actual function itself. Though again, for different values of A, B, H, and C. And what I did over here as usual is I plotted the residuals, again these vertical displacements of the red points away from the blue graph. For example, these are the furthest away over here. And so they have the biggest positive residuals. They're above the graph as well. And again, this number is the sum of the squares of the residuals. If I take all these vertical distances here, square them, add them up, I get about that. And you can see these numbers are pretty small, so it's not so surprising that that's not a very large number. You square a number between 0 and 1, it gets smaller. If you square a number between -1 and 1, in fact, it gets closer to 0. Anyway, the way I approached solving this problem and trying to find a good fit was just adjusting these parameters. Okay? Adjusting the amplitude, adjusting the angular frequency. You can see sometimes it does very badly if I make wild adjustments of B. Adjust the horizontal shift, and adjust the vertical shift. And you notice the residual graph can get far away from 0, and the sum of the squared residuals can get kind of high. I'm trying to minimize that. The best fit is to try to minimize that. And let me try to find the values of A, B, H, and C that you get to see on the board. So about 3.345 for A, somewhere right about here. Then B was about 0.0174, right around in here. Then H is about 79.88, it's pretty close already. Now adjust C. Something's wrong here. 4, 5, 6. Okay, I'm not sure what's wrong. I thought I had good numbers here, but it doesn't seem like they're doing a very good job. Oh, that's better. B seems to have the biggest effect, initially. Okay. I'm not matching the numbers that are on the board here very well. But you can see that those residuals now are fairly small. That sum of the squared residuals is fairly small. I'm trying to make it as small as possible. I'm trying to find A, B, H, and C in this interactive way to make that number as small as possible. And the idea is that's going to give me the best fit of the data. This is the kind of stuff applied mathematicians, statisticians do all the time. data modeling. You could even say it's part of data science. Again, like I mentioned last time, it's still not ideal because you really want random residuals, not residuals with a pattern. So it's not the best because of that, but it's pretty good still. You can see fit is pretty good of the data with this blue curve. That's all I wanted to say today about that. Let's go to the main content now. And we may use Mathematica sometimes with this main content. So again, we're looking at limits and continuity in the context of examples. So this is the rational function example from lecture 8B, the second lecture on Wednesday. Was that formula? Remember that? That's a rational function. It's a ratio of two polynomials. And remember I said the first thing you should do is try to factor the top and the bottom. And we can factor it like that. Then cancel any common factors. In this case, there is a common factor of x minus 4. If you pick random examples, there won't be any common factors typically. But here, because I'm the teacher and I'm picking the example, I can make it have common factors that can be canceled. To make a point, to make an educational point about this, it simplifies to x plus 1 over x minus 6 if what? What's the condition? If x is not equal to 4. Why? Well, that thing is defined at 4. It's got a value of 4. 5 over negative 2, negative 5 halves. This thing, these two things are undefined at 4. You'd be dividing by 0. So these things do not equal each other for all x. They equal each other for all x except 4, where this one is undefined and that one is negative 5 halves. If you graph this one, in and of itself, it's got no holes in its graph. But this one does, at x equals 4. Here's the graph. Better graph than I drew in class, okay? Think about the simplified form. It's got a root at negative 1. X equals negative 1 makes the top equal to 0. That's an x-intercept right there at negative 1. Zoom in with the camera if you need. It's got a vertical asymptote at x equals 6. Even in the simplified form, we did not cancel the x minus 6. You'd be dividing by 0 if you plug in x equals 6. There is a vertical asymptote there. But there is, I am trying to graph the original function, so technically there's a hole in the graph at x equals 4. But the limit exists. The limit of the original function as x approaches 4, either from the left or from the right, exists and equals the second coordinate of the missing point. The second coordinate happens to be the value of this function at x equals 4, which was negative 5 halves. Negative 2.5 is the second coordinate. You see the negative 2 right there and the negative 3 right there. Sorry if you're in back and you can't quite see the numbers here. That's negative 2.5 is the second coordinate of the missing point on this graph. But the limit exists. The limit is negative 2.5. Here are some limiting facts you can say. The limit of this function as x approaches plus or minus infinity is 1. There's a horizontal asymptote at this dashed horizontal line. Y equals 1. And what I said you could take to the bank on Wednesday is that when you're looking at a rational function like this where the degree of the top and the bottom are the same as they are here, whether you think about it like that or like that actually, the limit is the ratio of the coefficients of the highest powers. The highest powers over here are squares. Their coefficients are 1 and 1. 1 divided by 1 is 1. Same thing here. The highest powers are first powers. They're the same. The coefficients are 1 and 1. 1 divided by 1 is 1. Intuitively, when x is large, this is not a proof, but intuitively, when x is large, this is approximately x over x. Because the negative 1 and the minus 1 and the minus 6 don't matter much when x is large. And by large, I mean far to the right, positive large number, or far to the left, negative large number. A million over here or a negative a million over there, for example. They don't matter much. And x divided by x is 1. That's the intuition behind why the limit is 1. and it's a horizontal asymptote. There's vertical asymptote at 6. Don't misunderstand my notation here. I'm just trying to save some time in writing. This is really two one-sided limits that I'm writing. The limit as x goes to 6 from the right, focus on the plus sign, is plus infinity. The first thing there matches with the first one there. The top plus matches with the top plus. As you approach 6 from the right, through values that are 11 and 10 and 9 and 8 and 7 and 6.5 and 6.1 and 6.001, etc., the outputs go up forever and ever. They get above any horizontal line. They're going off to plus infinity, we say. And again, that doesn't mean infinity is a number. Okay? It just means it's unbounded. It's going up forever and ever. It gets above any horizontal line. On the other hand, if you let x approach 6 from the left, think of this minus sign there. If you were actually going to write it by hand, you'd probably put it a little higher. So you write it more like this. The limit as x approaches 6 from the right, you'd probably put the minus sign more up there. Excuse me, from the left is the minus sign. It's going down forever and ever. You write that as minus infinity. Again, not that minus infinity is a number, it just means it's going down forever and ever. It's below any horizontal line. As far as approaching the horizontal asymptotes, it gets arbitrarily close to the horizontal asymptote if you make x big enough to the right or to the left. Technically, f of x is undefined, the original function I'm talking about, at both 4 and 6. There's a discontinuity at 4, there's a discontinuity at 6. It's not even defined at 6. It's also not defined at 4. The original function I'm talking about, not the simplified version. The simplified version over here only has a discontinuity at 6. The limit as you approach 4, whether it's a one-sided limit from the right or from the left, or a two-sided limit, equals -5/2. You approach the same second coordinate here, -5/2. Whether you approach 4 from the left or from the right, that red graph is approaching that missing point. The y values are approaching the y coordinate, the missing point, -5/2. But that does not equal the original function value. Again, thinking of this formula as being the original function, not the simplified version. But because that limit exists, we say f has a removable discontinuity at 4. I could fill in the hole and I'd remove the discontinuity. I could define that original function in a piecewise way. I could say it equals this formula when x is not 4, and it equals -5/2 when x is 4. And it would fill in the hole. And it really would be the same as this function. It's a removable discontinuity. But technically speaking, in the original function, there's a discontinuity. Here's a second example. Here's its formula. I made the bottom a cubic now. Yikes. Factor it. I did make it possible. That doesn't mean it's easy. I did make it possible to factor it. If you had to factor it, actually Mathematica can do it. I'll show you Mathematica here. You can use a function called factor. I'm showing you some new things in Mathematica here right now. What cubic is it again? It's focused on the bottom here. It's x cubed minus 20x squared plus 124x minus 240. X squared minus 20, x cubed minus 20x squared minus 20x squared. What was it? Plus 124x minus 240. Is that right? No, you're forgetting. Mathematica, factor that. There, it did it. It wrote it in kind of a strange way with the x's second and the numbers first. But that is the factored form of it. X minus 4 times x minus 6 times x minus 10 is going backwards. Doesn't matter. And that's what I wrote in the PowerPoint. And the top is actually the same numerator as before. And factors as before is x minus 4 becomes x plus 1. So once again, I picked an example where you can cancel. You can cancel the x minus 4s here and simplify this function to that. And if you want, you could expand the bottom out there and get a quadratic. X squared minus 16x plus 6. If you wanted to. That would be the bottom, the denominator of the fraction. If what? If, once again, x is not 4. So the original function is undefined at 4, but the simplified version is defined at 4. It is going to be continuous at 4. Therefore, their limiting values as x approaches 4 are the same. The limit of this function, the original function even, f of x, where f of x means this original function, quadratic divided by cubic, is the same as the limit as x approaches 4 of the simplified version, x plus 1 over x minus 6 times x minus 10. Why? Well, even though this original function is undefined at 4, remember I said on Wednesday that technically speaking, the value of the limit doesn't depend on the function value at 4. That doesn't mean it's guaranteed to exist, but it doesn't depend on the function value at 4. It doesn't depend on the fact that this function, the original one, is undefined at 4. Only when x is very close to 4 but not equal to 4 is what affects the limit. But these two functions, this one and the simplified version, are the same function as long as x is not equal to 4, including when x is really, really close to 4 but not equal to it, 3.999 or 4.001. They're the same function, so they're going to have the same limiting values. And this one is defined at 4. It is, in fact, continuous at 4. And it turns out that means you can evaluate the limit by plugging in 4. And if you do, you get 4 plus 1 is 5, 4 minus 6 is negative 2, 4 minus 10 is negative 6. You get 5/12. What does the graph look like? Looks like this. This is the graph of the original function because I put a hole there. Try to make that circle a little more complete in my hole, but Mathematica was fighting me on that. There's a hole in the graph of the original function at x equals 4, really a point missing. I mean, this graph is actually a little misleading, right? Because points don't have any area. So the point is much, much smaller than I've drawn it, the point that's missing. You can't literally draw them, actually, but you gotta use your imagination. What's the second coordinate of this point? It is less than 1. 5/12 is less than 1, a little less than a half. Yeah, the second coordinate of that point is a little less than a half. This function does have a limit as x approaches 4. It does not have a limit as a number, at least, as x approaches 6 or 10. There are vertical asymptotes there. And there's a horizontal asymptote, I hope you can tell, at y equals 0 here. This blue dashed line that's horizontal. Looks like it's a little bit below the x-axis, but it actually is meant to be y equals 0. It is meant to be the x-axis. In a sense, it's nice we can still see it. Even though you might say it's a little inaccurate. There is a horizontal asymptote at y equals 0. As x approaches either plus infinity or minus infinity. How is that determined? Well, in this case, the degree of the top and the bottom, numerator and denominator, are different. The degree of the bottom is bigger. In that case, when the degree of the bottom is bigger than the top, the horizontal asymptote is going to be at y equals 0. The limit that you see there is going to be 0. And the degree of the bottom is bigger than the degree of the top. Intuitively, and again, this is not a proof, when x is large, either positively or negatively, The lower power terms of x don't matter. Think about the dominance. The x squared term dominates in the top and the x cubed dominates in the bottom. And that function is therefore approximately x squared over x cubed, which simplifies to 1 over x when x is large. And when I say when x is large, I mean positively or negatively. It might be better to put absolute value signs in there. That might be a better way to say that. And when x is large, this is close to 0, right? 1 divided by a million is very close to 0. 1 divided by a googol is much closer to 0. 1 divided by negative a googol is also very close to 0. So the bottom goes to infinity, so to speak, much faster than the top of the fraction, making the whole fraction go to 0. Same with the simplified form. The top has degree 1, the bottom one has degree 2. As you approach 6, you go up to plus infinity. That's a typo. I was looking for typos ahead of time, but I didn't catch this one. There's a vertical asymptote at 6. If you approach 6 from the left, the minus sign, you can see we're going off to plus infinity. As you approach 6 from the right, you can see we're going off to minus infinity. So the typo here, and I probably shouldn't write it on the wall. There should be a minus plus here. Let me write it here. What I mean by that is as x approaches 6 from the right, plus, the graph is going down forever and ever. It's going minus infinity, so the plus sign here matches the minus sign there. And as x approaches 6 from the left, imagine the minus sign is the only thing there. Then the answer is plus infinity. As you approach 6 from the left, the graph goes up forever. That was a typo. And that's how to fix it. If you want to write that down before I put this on the shared drive, I'll fix it. Put space in there, almost like I had something in there. But for the 10, vertical asymptote of 10, if you approach 10 from the right, plus sign there, through values like 13, 12, 11, 10.5, 10.1, 10.01, you can see the graph goes up forever and ever. The plus sign here matches the plus sign there. And as you approach 10 from the left, the graph goes down forever and ever. The minus sign here matches the minus sign there. The original function is undefined and also therefore discontinuous at 3 points, not just 6 and 10, but also 4. But the limit as you approach 4, whether you consider it to be the two one-sided limits or the two-sided limits, are all equal to 5/12ths, which does not equal f of 4 because, again, f of 4 is undefined. But because the limit exists, that discontinuity there is removable. I can fill in the missing point if I wanted to. And effectively, this simplified formula does fill the missing point. If you graph the simplified one, that point would be filled in. By the way, you read about this, and I think I have mentioned it. The only way the two-sided limit exists is if both one-sided limits exist and are equal to each other. The graph I drew near the end of class on Wednesday was an example where both one-sided limits existed, but they're not equal to each other because you have this jump discontinuity. And therefore, the two-sided limit, the regular limit, does not exist. The one-sided limits do exist. The two-sided limits does not, because the one-sided limits are not equal to each other. I think I have this one to be 8 and this one to be 12. And by the way, the value of the function at that value of x, it doesn't matter what it is. It could be this point, it could be this point, it could be this point, it could be any other point. It doesn't affect the limiting values of the one-sided limits in this picture. Because the value of the function at, I think it was maybe 5, doesn't matter. It's irrelevant. No, this function actually does cross its horizontal asymptote. I mentioned that. Yes, functions can cross their horizontal asymptotes. This one does, actually. Horizontal asymptote at y equals 0. It does have an x-intercept at -1. Right there, it's crossing the blue line. Since it's a horizontal asymptote, I guess that means it's got to go down and then back up again. It's hard to tell because it's so close to 0 there, but that is what happens. This red graph, as x moves to the left of -1, goes down a bit before coming back up again toward the horizontal asymptote. Just can't see it real well. So yes, graphs can cross horizontal asymptotes. They can even touch vertical asymptotes because you can make them piecewise. I could define this function at 6 to be, for example, -2. I could put a red dot right there, and then it's touched its vertical asymptote. That's really modifying the formula to make it piecewise, but so in a sense it's cheating, you might say, but you could do that if you want. Yeah? Why did it cross right here?
Yeah.
Because the value of the function at -1 is 0. There's an x plus 1 in the numerators. When you plug in -1, you get 0. So it's crossing this blue dashed line at y equals 0 when x is -1. It's above it over here, it's below it over here. And that's got to be the only x-intercept because of the factored form in simplified form. Third example. This time I took the exact same function from the previous slide and I flipped it. So that the numerator has a bigger degree than the denominator, but the factored form of this is exactly the same flipped. And once again, there's a common factor of x minus 4 that can be canceled as long as x is not equal to 4. Moreover, I also did something else to write the function in a different way. What did I do there? I did some polynomial long division to get this last thing here. It's not something I'm going to require you to know for the first exam. It is something worth learning. I'm not going to test you on it. There are videos about how to do polynomial long division, maybe on Khan Academy, for example. You can use Mathematica to do the division for you. I'll go back to the slide here in a minute. What I want to do is I want to divide this thing by, well, let's actually use the simplified version. The lines go away, I don't know. X minus 6 times x minus 10, that's the x squared minus 16x plus 60. X squared minus 16x plus 60 divided by x plus 1. When you use this polynomial quotient thing, you also have to put an extra x in there to sort of emphasize x is the variable that you're thinking about here, just in case you have more than one variable in there. That's the quotient, x minus 17. When you do the division, there's the x minus 17 right there. But then you have to add on the remainder of the long division, which is going to end up being 77 divided by the thing you originally divided by. And again, there's, for some reason in this view, you don't see the horizontal lines there. To find out remainder with Mathematica, you can do polynomial remainder. You just copy and paste this code, change the word quotient to remainder. 77. So what I'm telling you is if you did polynomial long division with this thing, that means you can write it as the quotient, x minus 17, plus the remainder divided by the original thing you were dividing by, the original denominator. I forget what that's called, like a dividend or something like that. The thing you originally divided by. I did that because it helps you figure out the graph. The graph ends up looking like this. And it's got slant asymptotes. It has no horizontal asymptotes. And that's something you can take to the bank as well. If the degree of the top is bigger than the degree of the bottom, then there are no horizontal asymptotes. If the degree of the top is 1 bigger than the degree of the bottom, like this one is, there will be a slant asymptote. This dashed blue line that's slanted is the slant asymptote. What's the equation of that line? It's the x minus 17. That line's got a slope of 1 and a y-intercept of 17. And it is the slant asymptote for this rational function in red here. It's approaching that slanted line as x goes to plus or minus infinity. And here's the way you could write that. The limit as x goes to plus or minus infinity of the function minus the slant asymptote is 0. That means these two things are getting closer and closer together as x gets bigger positively or negatively. Okay. So that's a way you can write that in limit notation. There is a vertical asymptote at -1. This dashed blue line is at x equals -1. It is to the left of the y-axis, as you can see, and that's no illusion. That should be the case. That's when x equals -1. That's a vertical asymptote. As you approach -1 from the right, you can see the graph's going up forever and ever. You put a plus infinity. Again, the plus there now matches the plus there. As you approach -1 from the left, this part of the graph goes down to minus infinity. So this minus sign matches the minus sign there. This is not the best notation to use, but I think it explained what I meant to. I'm considering two different one-sided limits when I wrote that at once. Just to save a little time, mostly. The original function is undefined at 4. There's a hole in the graph of the original function at 4, right there. But the limit as you approach 4 does exist. The one-sided limits exist and are equal, and are both equal to 12/5. Hey, I wonder if it's an accident that that's the reciprocal of the other one. No, it's no accident. It's because I took the reciprocal of the previous example for this example. But because those limits exist, I could fill in the hole if I wanted to. The discontinuity is removable. Once again, for emphasis, if I were to graph the simplified formulas, they would be defined at 4. I would fill in the hole. Question?
How did you get the slant asymptote?
I used the long division, which I'm not explaining how to do long division. Again, it is a skill worth knowing. Long division of polynomials, if you need to do more math beyond this course, say. I could test you on it, but it's sort of not our main focus. So I use Mathematica to do the polynomial quotient. That would be x minus 17, and then the polynomial remainder was the 77. I also have to divide the 77 by the original x plus 1 that was divided by. You can check. You should take the time to check. I often say this after class. Check that if you combine these, you'll get that. You get a common denominator of x plus 1. In other words, with this x minus 17, write it as x minus 17 times x plus 1 over x plus 1. Simplify, you should get this. Maybe with the top equaling x squared minus 16x plus 16.
Why is the remainder not considered as a part of this limit?
Yeah, good question. It's because as x goes to plus or minus infinity, as x gets big, this gets small. You got a constant 77 divided by something that's getting big either positively or negatively. Imagine plugging in x equals a million here. 77 divided by a million and 1 is very small. Plug in x equals negative a million, you got 77 divided by negative 999,999. Also very small, very close to 0. So this term doesn't matter in the long run as x gets big. That term does. This is dominant in the sense of that. Good question. Thanks for asking. Some kind of funny examples come next here. We'll do this slide and then take our break. Here's an example involving the absolute value function. Take the absolute value of x divided by x, which can also be written as the square root of x squared divided by x. Remember, I think I said one day? Some people think the square root of x squared is x, but they're actually wrong. It's only x for when x is not negative. If you want this to be true, including for negative x values, you need the absolute value signs. which, by the way, can also be written in a piecewise way. The absolute value of the number x equals x itself if x is greater than or equal to 0, and it equals the opposite of x if x is less than 0. And if x is negative, the opposite of x is actually positive. The absolute value of negative 5 is negative of negative 5, which is positive 5. So you can write the formula in a piecewise way too. So to think about graphing this function, you really need to think about two cases. What if x is positive and what if x is negative? And you don't want to plug in x equals 0 because you'd be dividing by 0. If x is positive, it's really x over x, which simplifies to 1. If x is negative, it's really the opposite of x divided by x, which simplifies to negative 1. The graph consists of two horizontal lines that looks like this. And for emphasis, the points 0, 1, and 0, negative 1 are not part of the graph, so I made open circles. Even though points are infinitesimally small. I'm trying to emphasize that the points with those coordinates are not part of the graph. This function's got a horizontal asymptote at 1, but also a horizontal asymptote at negative 1. Two horizontal asymptotes. One as x goes to plus infinity to the right forever and ever, and one as x goes to minus infinity to the left forever and ever. This one crosses its horizontal asymptotes infinitely many times because it's equal to its horizontal asymptotes for appropriate values of x. So it's not an asymptote in the usual sense, but those limit equations are still true. As x approaches 0 from the right, the y-coordinates are always 1, and so the limit is 1. As x approaches 0 from the left, the y-coordinates are always negative 1, and so the limit is also negative 1. Those two one-sided limits exist, but they're not equal to each other. Therefore, the ordinary two-sided limit does not exist. Because the one-sided limits have to equal each other for the two-sided limit to exist. Let's take a break.